trees to non-tree graphs. We still have essentially readings that I hope most of you have actually read at this point, which is treeinfants.pdf, which has been posted on the web page. And like I said before, pretty much everything that we're talking about today, including the figures and sometimes exact sentence quotations, come from this write-up. So if you read that and understand that, you'll understand everything that we've talked about. So here we are in lecture 3. Forgot to update that. So let's do a little bit of review before we go forward to sort of highlight the main points of last lecture. And you might think, for example, on YouTube, why should I even do these reviews since everything has been recorded? But I thought about that, and I think there's a utility to the reviews because it sort of is an attempt to try to summarize the last lecture. And so if, for example, you watch the last lecture and then you watch the beginning of the next lecture, that will be sort of a recap of everything that perhaps is most important about the last lecture. So therefore, there's utility in having these reviews, even for those of you who are not watching this lecture live. So the first thing that we did was we talked about this notion of families and how a graphical model corresponds to a subfamily of probability distributions that satisfy certain properties. And we spoke about various different ways of defining families, and in particular 2 ways, defining families either based on the maximum cliques or based on the cliques in the graph. And we had these 2 families defined, and we wanted to see how these things compare. And in this particular case, this was a very simple case, we saw that the families were the same. But in general, when we define a graphical model and we define a set of Markov properties or rules or semantics associated with that graph, we might get a very, very different family, which might not have such a simplistic relationship with other families of probability distributions. And much of what graphical model theory is about is developing new ways of using graphs and developing semantics to carve out subfamilies, useful subfamilies, from large collections of probability distributions. Okay, the next thing we did is we defined a tree. And we saw that there are lots of different ways of defining a tree. One way that I think I'd like to highlight is this last one, which is that a tree can be generated by starting with a single vertex and then adding another vertex and connecting it with one edge to some existing vertex. And since each time we add an edge, we're never connecting it to 2 vertices, we're always going to have a tree. And any tree can be generated in that fashion. And the astute listener will have perhaps noticed that when we generate a tree in that way, notice that the very, very last node that we instantiate, that we produce in this tree, ends up being a leaf node. And if we then run the elimination algorithm, the graph elimination algorithm, in the reverse order that we generated this tree, that will be an elimination order that results in this R² cost. That basically means that there's no additional fill-in edges that are caused by running elimination in the order that is the reverse of the way that we're generating the tree in this last bullet point in this definition of a tree. So that's not a coincidence that those 2 things are the same. Okay. We also saw how if we have a tree, the clique sizes are of size 2, and the max clique sizes are of size 2. And we saw that if we take any additional set, if we take a set of nodes of size greater than 2, then we get a forest. And we also saw how chains are trees. And we started by looking at chains, which corresponds to things like Markov chains, and marginalizing out, for example, the idea that we have a joint distribution over a chain here, and we marginalize out with this sum, and we get a distribution over some subset of the variables. In this particular case, x3 and x4, which corresponds to an edge in the chain, because these are successive nodes. And we saw how basically, if we do this, such that in the chain, if we do it on either end, first of all, it's a tree, and those are always the 2 leaf nodes in the tree, in that particular case in a chain. But if we do it from outward to inward, we're never going to couple together any factors that perhaps don't need to be coupled together. But on the other hand, if we were to eliminate any interior vertex in the chain, we would couple together vertices that need not be coupled together and correspondingly have an increase in computation. Namely, we'd go from r squared to r cubed. And basically that corresponds to this problem, which is that in general, once you've marginalized out a variable, b in this case, we get a factor which doesn't further decompose into two factors amongst the remaining variables, a and c in this case. And more generally, if it's a vector, like if x of b is a vector of variables, we sum out that vector, we are inextricably coupling together the residual variables xa and xc. Now in the tree we saw that this isn't necessary to do, but we also started implying and hinting at, and actually more than hinting, showing examples of where when you do this in equation 3.18, we end up coupling together stuff, which graphically means that when we couple these things together, the graphical representation of that coupling should be a clique, because a clique is basically the stuff that says you are allowed to have a factor which doesn't further decompose. The clique allows that to happen. If you have a clique amongst three variables, you can have a factor amongst those three variables that don't factor, that don't or that don't decouple in this way. And we define this notion of elimination. And the idea, this is sort of an informal definition, to eliminate a node in an undirected graph, we first connect all of its neighbors and then remove that node and all of the edges that are incident to that node, v. And then once we have done that elimination step, v, once we've eliminated v, these former neighbors now form a clique because they are now fully connected. And there might be additional edges that are added, and any additional edges that are added as we go through this process of eliminating variables are called fill-in edges. And here's a slightly more formal description of the process of elimination. This was not from last time, but this is just a new slide. And it uses a notation that says, let's say delta sub g of v correspond to the neighbors of v in the graph G. Okay? And when we eliminate a node v, that's the vertex set of graph G, we form a new graph G1. So G1, what is G1? So G1, first of all, consists of the vertex set V1 and the edge set E1. Okay? The vertex set is the original vertex set V without the vertex that we've just eliminated, lowercase v. Okay? And the edge set, E1 of this graph G1, corresponds to the original edges, but where we've removed anything, we've removed any edge that involves the vertex v that we've just eliminated. But then we've added all edges corresponding to the neighbors of v in the graph within which v was originally eliminated, which is this last bit over here. And that is where we get this clique, because basically delta g of v cross delta v of g, those are basically all pairs, and those are all of the edges between any of the nodes that were a neighbor of v in the graph G. And so that basically means that v's neighbors in the former graph form a clique in this new graph G1. And that's basically what this is saying. In G1, delta g of v forms a clique. And the fill-in edges in this elimination step correspond to any of the edges in G1 that are not in G. Because basically this is a union. This guy here is a union. It could be the case that some of those edges, or perhaps all of those edges, already exist, in which case there's no additional fill-in edges. But it definitely must be a clique if there aren't any fill-in edges. The clique is there already. We happen to be lucky in the sense that we haven't, because we know that when we add edges, the family can grow, or the family will grow, and if anything, that's generally not a good thing, because it means that we're solving something for a family bigger than perhaps is necessary. Perhaps, not necessarily is necessary, but perhaps is necessary. And so notationally what we can do is say, okay, well G1 is this graph G with sigma 1. So this notion of, we have this string of sigmas. So sigma is like, let's just define this up here. Sigma is just an ordering. Of the vertices. Or it's a permutation of the vertices. And it's an ordering of the vertices, and that's the ordering that we eliminate the vertices in when we eliminate all the nodes. And then when we do this elimination order, when we find this ordering and we do the elimination in the order of that of that ordering, we end up getting this series of graphs. So G1 is the graph that results from eliminating the first vertex. G2 is the graph that results when we eliminate the second vertex, and so on and so forth. And so we get this series of graphs where G0 is the original graph, and Gn minus 1 consists of only one vertex, the final vertex in that ordering. And then along the way, every time we've eliminated a vertex, we maybe have introduced some new edges. Any of those new edges that we've introduced, union together, constitute this fill-in. And so in the reconstituted graph G prime, we have, it's the original node set, the original vertices V, the original edge set E, union together with any additional fill-in that we've got. So what is the unique property of a tree then? The tree is such that because there's always a leaf node, in fact there's always two leaf nodes, a tree is such that we can always eliminate in an order such that F is equal to the empty set. Okay. Question for you guys. Do you think that's the only graph, the only type of graph where, so we saw, all right, first of all, we saw in a tree that, is it necessary for any ordering that F is equal to the empty set in a tree? No, we saw that. We've eliminated this interior node that has multiple neighbors that are not connected. We eliminate it. We can create some massive clique. Imagine if we had a star. A star is a tree. Here's a star. Or a spoke, a bicycle wheel, hub. Right? That's a tree. If you eliminate that center vertex, suddenly all of the remaining, all n minus 1 of the remaining vertices become coupled together in a clique. So in this particular case, in this star graph, we would go from r squared computation to exponential, right? That would exponential in the number of vertices, right? It would be r to the n or something. So that basically means that not all orders are created the same. But on the other hand, you see that in this star graph, there are obviously lots of leaf nodes to choose from first. So then the question, getting back to this question to ask you, is the following. Are trees the only graphs for which there exists an elimination ordering that produces no fill-in? Sorry? Right, that's very good. A fully connected graph. Or what if you just start with a clique? Right? So a clique obviously has all edges. So if you eliminate in any ordering, then no fill-in will be produced since there's never any fill-in. But are those the only extremes, either a tree or a clique?
Is it true that if you...
No. It's not the only two. So we will... No. We will study them. So we're not going to get at this today, but the class of graphs called triangulated graphs or chordal graphs are exactly those graphs for which there exists an ordering that can be used to eliminate the vertices, all of the vertices, which produces no fill-in. Now, I said before that, and this is, I guess I'm sort of giving away the punchline of this set of lectures, but sometimes it's useful pedagogically to give away punchlines even though its comedic value is reduced. So I will not put priority over comedic value at the expense of pedagogical value. So the punchline that I'm giving away is the following, is that the chordal graphs, the graphs basically that are such that there exists an ordering that doesn't produce any fill-in, correspond also to the graphs that can be embedded into a tree of a certain kind, and we get back pretty much the same thing that we started with the tree. So if you're wondering why we're spending today and probably some of the next lecture on trees, it's because from the perspective of what you can do with exact inference, pretty much everything is a tree. So next time you go outside and you look at your walnut tree or something, you will look at it and you see it with renewed respect. Not only does such a structure offer us nourishment, but it also offers us computational tractability. Question?
Is it true that if you take the quotient of a graph with a max clique and then continue on in sequence, you get a tree? Or
Did you say what did you say of a graph?
the quotient.
Quotient. So how do you define precisely that?
Uh, well, everything inside the clique is part of one Collatz class, and everything outside. You just shrink everything inside the clique into one. Like,
Roughly speaking, yes,
Yeah.
that is correct.
is
Yes.
that correct?
That's roughly, yeah, roughly speaking. There's a little bit of nuance there that just this interchange between us has glossed over, but that's essentially correct. So, okay, so the other thing, this is again review still. We're doing a lot of review. I hope this is useful. We saw some examples of eliminating nodes, and here we eliminated this node, which created this edge, and when we reconstitute, we get this 3 cycle. We started in the 4 cycle. 4 cycle is a very important example that we will visit a number of times. So any node that we eliminate corresponds to something that will induce a fill-in. In this particular case, it creates that fill-in, which when we reconstitute the graph creates this. One thing actually that might be worth talking about in this graph. So now once we've got this reconstituted graph, there are 2 nodes now that we can eliminate that don't create fill-in. We could eliminate that guy. And this edge already is there, right? So what we're going to see today is that once we've gone through the process of elimination of a graph and reconstitute it, now in that reconstituted graph, does there exist an ordering that induces no fill-in? In this graph, it certainly does. In fact, we could eliminate x4 first. That doesn't produce any fill-in. Or we could eliminate x2 first. And that also wouldn't produce any fill-in. And once we eliminate x2 or x4, the rest obviously doesn't produce any fill-in. On the other hand, it doesn't mean that all orders, it's not a clique, it doesn't mean that all orders would produce no fill-in. This guy, if we eliminated that, that would produce this fill-in. So it's not allowing all orders to occur. But it basically implies or maybe suggests that if we've gone through the process of elimination, suffered any consequent fill-in that happens as a result of that elimination, reconstitute the graph, maybe once we do elimination again, or maybe it won't cause any fill-in. In fact, that's going to turn out to be true.
And that must be a chordograph.
We will see that, yes, that corresponds to a condition on chordality. That's exactly right. Yep.
So intuitively, would it make most sense to just eliminate the nodes of the graph that have the lowest degrees first?
That's a good heuristic. If we eliminate the graph with the lowest degrees, is that always going to create the least fill-in if such a thing exists? It's a little bit tricky. So that turns out to be one of a set of standard heuristics. But it turns out that in general, it's hard. That's a hard problem. And that heuristic isn't guaranteed to be optimal, strangely enough. But we will get to that. That will probably be Wednesday's lecture, possibly in Monday's lecture. We will talk about elimination heuristics. There are a number of computationally complex, NP-complete hard problems that we will run up against, which will be depressing because, on the one hand, these problems for these graphical strategies that we're going to be pursuing to produce a method to do probabilistic inference are nice because it's purely algorithmic. But at the same time, just because something's algorithmic doesn't mean it's easy. It might be the case that finding the strategy that leads to the optimal strategy for doing inference might itself be NP hard. And this is one case where that would be the case. So what else do we know about trees? OK. It always has 2 leaf nodes. Eliminating a leaf node always yields a subtree. We can continue eliminating nodes in a tree graph. Eliminating leaf nodes never produces any fill-in edges of a tree. Data structures for leaf nodes is easy. And this all, we're doing this all graphically, but the whole thing corresponds to computation because we're summing out variables. The whole thing is order nr squared, right? which is good. Now, the other thing that we started doing is we wanted to talk about belief propagation. And belief propagation turns out to be essentially elimination, as you will see. So when we're doing this elimination, like we eliminate up, we're sort of rooting the tree. This is sort of a non-standard notion of rooting a tree. You don't usually root a tree at an edge, but I'm just doing this for sort of illustrative purposes. We're kind of, in some sense, rooting the tree at this edge. The reason being that we're interested in that marginal, and so everything is we're eliminating towards that edge, x1, x2. And so when we do this elimination step, or start doing elimination step, we can sort of see this as a set of messages. And this is would be an ordering that we would do that. And we saw that also last time, that each one of these little elimination steps, like x14 corresponds to this elimination step, and maybe x7 corresponds to this elimination step. And I don't think I need to do all of these, but let's do x15. I'm going to start needing glasses for doing this. Corresponds to this one. So each message corresponds to a computation, which notationally we were using this sort of crossing off business, which, as you can imagine, when you've got hundreds of thousands of vertices in your graph, becomes very tedious. And if you were to, for example, write it down on a paper, your entire paper would be a series of numbers crossed off. That wouldn't be a paper that would likely to be accepted at NIPS. So in order to be accepted at NIPS, we are going to use a different notation. But basically, the idea is the following. So a vertex, in any of these cases, each vertex, in some sense, receives a message from the children in this rooted tree, right? Like, here's the rooted tree. Like, take this guy, for example. Once he's received this message, these two messages, from x10 and x11, then he's sort of free to continue on. The reason why is because once he's received the messages from his children, once x4 has received a message from his children, x4 becomes a leaf, right? Because all this stuff down here is gone, kind of. That's gone. It's been eliminated. So x4 is a leaf, and now we can eliminate x4. Now, the fact that x4 has had this history of having messages being sent to it is, to some extent, irrelevant from the perspective of the message being sent from x4 to x1, as long as it's the case that the consequences of of those former messages or those former elimination steps are somehow represented in the representation for what's going on at x4. And so, but the basic idea here is that a node I may send a message to a parent when it's received a message from all its children. That seems to be sort of the property that makes it possible to send a message, which corresponds to the property that we've eliminated all other leaf nodes, and now this other node, which formerly wasn't a leaf node, is a leaf node. And then the root, so the parent, what is a parent and what is a child? Remember, this is not a Bayesian network. This is just a rooted, undirected tree. And parents are basically those vertices on necessarily, the parent is your adjacent vertex, which is necessarily on the unique path between you towards the root, and the children are the ones that are away from the root. And so the last thing we did, this is still review, believe it or not, but the last thing we did is we defined this protocol, which is that a message may be sent from a vertex I to its neighbor only when the node I has received a message from all its other neighbors besides j. Okay. And here's the notation for that. I may be sent to j only if, for all k in the neighbors of I except for j, k has been sent to I already. And this protocol then defines a partial order on messages. This seems to be a property that, we can sort of think of this from the mathematical perspective of summing out and marginalizing variables, or you can think of it as a purely graph theoretic set of arrows. But we will get that no matter how we do this, no matter what order we do this in, as long as we respect the message passing protocol, we will get the correct marginal. So here are some examples. So this is finally new stuff. So let's say that this cloud structure here, the reason why it's a cloud is actually because we're going to generalize this. But I didn't want to redo the figure because I'm lazy. But basically, let's say a cloud is a vertex in a tree. Okay? And the blue edges are the edges. So what this is saying is I think you can see yellow. Can you see yellow and green? You can definitely see it on the screen, on the electronic screen. I'm not sure if you can see it on the optically projected screen, but assuming you can, assume that the yellow messages have already occurred. And in this first example, the green message is OK because we've received messages from all its other neighbors. The second example here, this is also OK. Even though we received an additional yellow message, as long as we received a message from all the other neighbors, we can send out. It's kind of like we've gotten everything from all of our other channels before we can send out to our other channel. Question?
So this is general. This is not for the tree anymore.
Well,
You wouldn't do this, right? You wouldn't go backward and forward again.
this is for the tree. This is for a tree. It's not general because if we do this strategy, you remember, it kind of doesn't make sense. Like imagine we had a cycle. Imagine say we start from a 4 cycle. How do we start? How do we start the message passing protocol with a 4 cycle? There's nowhere to start. No matter what node you look at in a 4 cycle, you've never received a message from its other neighbor to be able to send a message to its first neighbor, say. And so you're stuck. It's kind of like deadlock. It's what happens in downtown cities when everybody's stuck. You can't move because these guys can't move, and these guys can't move because these guys can't move, and these guys can't move because these guys, and you sort of, it's deadlock. Whereas when it's a tree, it's not a deadlock. In fact, for example, this third example shows precisely what happens at the leaf nodes. When this is a leaf node, this example here is a leaf node because it's saying, oh, you're a leaf node. You can start sending up towards the root. You're cool because there are no other neighbors, so there's nothing to receive from. So you're happy. You're perfectly happy to, or you're perfectly allowed to send messages. And then another example here is. Which is also OK. It's saying that the message passing protocol doesn't preclude the possibility of sending messages twice. So once you've sent a green message, in this example, let me zoom in on it. This is the top right. Once you've sent a green message here, you can send it again, at least according to the protocol. Where you'd be in error, so that's an error. You can't send that ren message because you haven't yet received a message from this direction. Similarly, you can't. So this is what would happen in the 4 cycle case. So every vertex would look like this in the 4 cycle. You can't send a message because you haven't received yet a message from here. This is also an error. So even though you received a message along that edge, you can't send out a message because it's with respect to all of the other neighbors, and you haven't received anything here. This is also OK. So you can send down to a leaf node and then propagate back up. So I think those are all of the key examples. Yes?
What does it mean to send a message twice? Would you just be sending the same message, or would you send 2 different messages?
Yeah, so we will talk about that. So let's define precisely what a message is, and then you'll see what a message is. The idea, I'll give you, just answer a little bit of this question now. It's like, you're this vertex, right, in this graph, suppose. I mean, you kind of look like a vertex. I mean, I look like an edge. But we all are edges or vertices. And there's 2 kinds of people in the world. There's edges or vertices, right? So let's say that you're a vertex, and you want to send a message. So the idea is that you have structure, you have sort of storage associated with you, associated with maybe the messages that have come in already. And then what you do is you take this data, storage that you've got, and you do some computation, and you send it off to some other node. Now doing it again would just mean doing exactly the same computational steps. Precisely what a message is, we've said so far that it corresponds to elimination, but so far in this elimination we have this long history of stuff, right? It's just these mathematical equations where these subscripts get very, very long, very fast. Let's now change the notation so that we can more properly define what a message is. And in fact, there's multiple kinds of messages, as we will see. We'll talk about 3 types today. But it's an unwieldy notation, but it's useful from the perspective of learning about elimination. But what we want to do is morph from the elimination notation to the message notation. So the message notation that we're going to use is the following. So mu I through I to j. So it's basically saying we're sending a message from vertex I to vertex j, and it's a function only of x of j. Okay? Because x of I, it's going to correspond to an elimination step where we are eliminating vertex I. So here's the 2 notations side by side. So before, what we did is we said, OK, we take this potential function here, we marginalize out x14, and we have this notation phi, which has 14 crossed off. Now what we're going to be doing is we're going to be calling it a message from 14 to 8. Okay. But what about the case when we get this long history of stuff? So here's an example of a message that corresponds to summing out x3 here. But in this particular case, we've had this message. The 9 came from somewhere else. So this is answering your question again, Mr. Vertex. We have this guy. You can think of that as some structure that you're storing locally at the, sorting the node. This guy and this guy here. Those are sort of local storage bits, which then we sort of multiply together with this table here. We do the summation, and we get this long message. We get this long result. But we're not going to sort of need to know all of this stuff. As long as we've obeyed the message passing protocol, we just assume that all of that stuff has been happened. And so we just call it, okay, that's a message from 3 to 1. From 3 to 1 because we've summed out 3, and we're essentially then going to store that array. That array, indexed by x1, is going to be stored, in some sense, at x1, at vertex 1. And so here's the generic form of a message then, at least according to what we've seen so far, that we construct all messages. First thing we do is we collect all messages from all neighbors of I other than j. So that's this stuff right here. Okay. The next thing we do is we incorporate these incoming messages by multiplying them along with this edge factor. And so that's basically this stuff up there. Okay. So that factor, the ij factor, is sort of like a communications channel between I and j. So we've sort of taken, you can think of the messages that say I has received. These are the messages that I has received. You can think of that as the information that I has received from its nodes other than j. And then there's the communications channel between I and j. And we package together the information that we received between I and j, between I and all of its other vertices, and the communications channel between I and j. And then we form a new message going to j, which is this last marginalization step, which is this bit. Okay? And that becomes the message at j, that's stored at j. Was it a question?
Oh yeah, I noticed that the factor we're using is r squared, and that we have no fill-in edges. Is it true that messages assume no fill-in edges, that we're doing this properly?
In the case that we do the message passing protocol, and we have a tree, there will not be any fill-in edges.
Okay.
So that's something that we're sort of seeing intuitively yet, but that should be a theorem. But when you think about it, in a tree, think about this inductively. When we do the message passing protocol, the first thing we can do is we root the tree somewhere. The only thing we can do when we start is send messages from the leaf nodes to the root, right? But then, what the message passing protocol says is that any node, in order to send a message towards the root, you need to have received the messages from all the other children. That means that all those other children have been eliminated, which, by induction says that all of its children's children must have been eliminated. And so basically that corresponds to a leaf node as well. So at every stage, we've received a message from all its other children, and we can propagate up to the root. And so the message passing protocol, therefore, if it's a tree, never has any fill-in edges because we're always eliminating leaf nodes. It's essentially the elimination process on a tree where we're only eliminating leaf nodes in the current graph, not in the original graph, because as we keep eliminating nodes, new leaf nodes are exposed, or I should say created. They're not exposed, they're created. Okay, so here's an important bit. So far, we've only been, question, yes? It's r squared. Sorry, I'm just kidding.
So there may be some quantities that we may want to compute that need not be computed in r squared itself, right? Like for example, if I want a factor that depends on some pair of non-adjacent nodes or
Yes.
something like that, then I may have to go through the entire graph.
Yes.
And
Yes. You're absolutely right, and you're anticipating a future slide. We have a slide exactly on that topic. So I could tell you now, or we could wait.
Okay.
So, But let's talk about this case. This isn't this case yet. This is the case when it's that there are multiple marginals that we want. So far we've only talked about there being one marginal, and we want to sort of root at that edge corresponding to that marginal, and we want to send messages to that marginal. What if we have a whole set of marginals and we want to compute p sub x of s for all s of I, and we have some set of s of I, s1 through sk? Okay. That means that, well, what we could do is we could do this process k times, right, independently. And if we had k processors, this would run in the same amount of time. But this is not a very smart way of doing it, as you will see, because there are ways of doing it much better. Okay. In fact, we can reduce it. Notice that we can reduce it to order nr squared, independent of k. And the way we do this is by removing redundant computations. And the basic idea is a form of dynamic programming. Essentially, all exact inference in graphical models is a form of dynamic programming, where what we do is we use steps that have been computed to solve one problem to solve another problem, because there's redundancy. There's steps that can be reused. And so here's just a simple example just to start out with. Let's say that we have this graph, and now we have two edge marginals that we care about. We want the original marginal that we were looking at before, the marginal over x1 and x2, which corresponds to the blue edge. And we also have this new marginal that we also want, x1 and x3. So like I said, we could just do the process that we talked about, do it twice, but that would be not smart. And here's, just to make sure that we're clear, here's what we could do if we did this naively. So if we wanted p of x1 and x2, we could use the following variable elimination order, where we first eliminate, say, x14, and then x7, and then x8, and then x9, and x15, and x10, and so on and so forth, up until we get to that edge. And that would correspond to this set of messages, right? So we've got 13 messages. The first one would be x14 to 8. Then this would be x7 to 3. Then x9, x8 to 3, and then x9 to 3, and so on and so forth. Now we're done. We've got the blue marginal. Now we want to get the red marginal, p of x1 and x3. And we could do the same thing. We come up with a variable elimination ordering, 4, 7, 8, 9, and so on and so forth. And then we look at the corresponding messages. And we have, again, x14 to 8, x7 to 3, x8 to 3, and so on. Now, have you noticed that a lot of these messages are the same? Like, look at this. This message is the same as this message. And this message is the same as this message. And so on and so forth. This message is the same as this message. So, in fact, the first 12 variables in each of these elimination orders are identical. And if we just do the first 12 variables in the elimination order, or send the corresponding first set of messages, what we end up getting is this marginal over x1, x2, and x3. That happens to be a subtree in the original tree. And once we've got the subtree, then getting the two marginals, the two desired marginals, is super easy. We just sum out either x2 or x3 from that marginal. And we've reused most of the computation. So here's another look at it of the same thing. This is, I mean, for some reason to me, this looks like a 4th of July graph, for those of you who are American. But don't you feel patriotic looking at these messages? I'm joking. Now I'm going to get myself into trouble if I start talking about this on video. So in any event, we see that many of the blue and the red messages are redundant, right? All of the edges, or most of the edges, have 2 arrows on them. The only ones that don't have 2 arrows are the ones that correspond exactly to the last 2 marginals that we talked about in the previous slide, namely the marginal over x1, x2, x3, where we sum out either x2 or x3. So in general, the amount of reuse depends on the desired queries. Like, for example, if we wanted to compute x8 and x14, the marginal over x8, x14, and over x6 and x13, we could start with this order. We could start with the order that says, OK, we'll first eliminate x7, and then x9, and then x15, and then 10, and then 11, and then 4, and then 5, and then 12. I think that's right. And so what we're left with is this residual graph. And that residual graph happens to be a path or a chain between x14 and x13. And then what we would do is we would do essentially the message passing procedure that we've seen done on chains, where we send messages from either x14 to x13 and then back to x14. And that would then give us the information necessary to do get the marginals, these two desired marginals up here. Now, this isn't as efficient as what we saw before, but what we've done at least is we sort of trimmed off these common branches, like this stuff here. The green stuff is the common branches. That's the redundant stuff. And rather than doing that twice, we've trimmed that off. And then what we're left with is a chain, which is in some sense the worst case. It has the least amount of potential reuse, since the queries that we want are on the ends of a chain. But it is still some savings, right? So we're trimming. This trimming of green stuff is useful. It cuts down on compute.
I think still it's fair to say that instead of n r squared, it's actually maximum to be 2 n r squared, because if it's a partial order, so the maximum computation you can do is that you do for one edge you do 2 computations.
Yeah, when I use big O notation, I'm not worried about 2.
I know, but
So
essentially instead of k n squared, r squared,
yeah, but 2 is a constant. It doesn't grow with n, right? So like what I was about to talk about, like when it's k, like the original redundant thing, it might be 2k n r squared, n r squared. I'm not worried about a factor of 2, at least not in big O notation. But what this case, however, is when k is equal to n. Okay, or when it's or n minus 1, I should say, because when k is equal to n minus 1, that would be, if I were to do this naive thing, the worst case, in which case the redundancy would grow with n. So since we're talking about the complexity with respect to the number of vertices in the graph, which is n, and the number of possible values of the random variables can take on, which is r, this would be, if I were to do this naively, order n squared r squared. Right? That I'm claiming, even, I said it's not a function of k, we can reduce that to order n r squared. And the reason essentially is that as the number of queries grows, the efficiency of this also grows. The efficiency is sort of measured in number of queries done per message. The efficiency grows as the number of queries that you want grows. And the way we do this is the following. We root the tree, at least intuitively at all edges. And anytime we follow the message passing protocol, anytime an edge is marked with an arrow, we never redundantly send that message. And when we're done with this whole process, the resulting tree has been so annotated with both directions along each edge marked. And once we have that, notice that, like, if we zoom in on this guy, say x2, x6, we have all of the information we need to compute that marginal. We need this message, this message, this message, and this message. So we need those yellow messages to compute the marginal over x2 and x6. And for any edge, basically, we have all of the information that we need to compute that marginal. You can think again in terms of the data structures, where every vertex has the set of messages that were sent to it. And if the message passing protocol is abided by, and if all edges have both directions marked, that every vertex has all of those pieces of information necessary, such that every edge and its incident 2 vertices has the necessary information to compute the marginal. And in fact, here is exactly the equation corresponding to that marginal. we're saying, okay, we've got the edge potential, this is for marginal ij. We've got the messages that have been sent to I except from j, and the messages that have been sent to j except from I. We multiply all that stuff together, and we get the marginal. Right. Now the whole computation is nr squared, or if you want to include the constant, it's 2nr squared. But again, it doesn't grow with n. It's a factor of 2 regardless of what n is. So it's a constant. It doesn't matter from the complexity theoretic perspective. Okay. All right, any questions? So we have this theorem which says that if the messages are sent obeying the message passing protocol, MPP, so that all edges have 2 messages across the edge in both directions, then the computation above will correctly produce all marginals. And the proof is very simple. We've sort of already given it. We've basically said, well, look, all of that information we have at those vertices is exactly what we would get if it was the case that we were just to root it at that edge and then just do elimination up to that edge. But that's true for any edge. And so therefore, it works for all edges. So then we have this message passing procedure, message passing protocol. The message passing protocol basically says, what can you do when? In other words, what is required, what must have been true in order for you to do the next step? But we would like to sort of instantiate that into an actual subroutine that maybe you could implement in MATLAB or Java or Ruby or whatever language you like. And so here's what we could do. We could choose an arbitrary root node. So now we're rooting at the node. We send messages from the leaves up into the root. And once the root has received all messages from the children, we start sending it back down to the children. So it's kind of like an in-order search. Or I should say, sorry, this is really officially a post-order search. When done, the claim is that if we abide by this protocol, then the message passing protocol will have been obeyed as well, and any marginal can be computed. And this is essentially the algorithm called collect evidence and distribute evidence. Now, raise your hand if you've ever heard of collect evidence and distribute evidence before. Okay, some of you might have heard of this. So normally, collect evidence and distribute evidence is defined in the context of what you do in a Bayesian network after you've converted the Bayesian network into an undirected graphical model and after you've triangulated the graphical model into a junction tree and all this kind of stuff. What we're doing is we're defining this procedure, collect and distribute evidence, directly on trees in an undirected graphical model first, just to sort of get the sense of what's going on. And then we will later, after we've gone through the process of converting general graphs into trees, revisit collect and distribute evidence. So just in case there's any confusion, this is not, this is, I think, a better way of sort of introducing the concept of collect and distribute evidence, just in terms of these trees on undirected graphs. So what is collect evidence? So it's an algorithm that you could implement in your favorite programming language, where you start with a rooted tree. And let's say it's called with an argument, which is a child and its parent. Okay, so this is like a subroutine. You can think of it as. And so it's called, the 2 arguments to the procedure are the child and the parent, and we're guaranteed that that's true. And then what we end up have as a result is that we have a message propagated from the child to the parent that obeys the message passing protocol. So what we do, the first thing we do is that for each child of the child, so you is the grandchild in some sense, for each grandchild, we call collect evidence from the grandchild to the child. And then what we do is we say, okay, well look, we've got all of the messages from our grandchild, and so we basically multiply them together, sum out the child, and we form the message going to the parent. That obeys the message passing protocol because, you know, if you're a rooted tree and you're a vertex, you have a set of children and one parent. Right? Your one parent is the unique direction towards the root. And so you've now gotten messages from all of the grandchildren, and now you can send a message to your parent. Distributed evidence is sort of the opposite. It's again a routine that has two arguments, P and C, a parent and a child. And what is the result is a message propagated from the parent to the child. And so all we do is we basically say that we collect together all messages that have been sent to the parent except for the child, and then we sum out the parent and we send it off to the child. And after we've done that, then we send a message to all of the grandchildren by calling distributed evidence recursively. So now that we have these two subroutines, we have the whole procedure, the collect distribute evidence algorithm. And we have a tree graph, and what the result is essentially all messages sent along all edges where all messages have obeyed the message passing protocol. So the way this works is we define an arbitrary root, it doesn't matter which one, and then for starting at the root, we do for each children, we call collect evidence. And since this is a post-order search, what this is going to do is propagate down to whatever the leaves are of this tree and start sending messages up from the leaves to the root. And once we've reached the root, then we start doing distributed evidence from the root down to the children. And just recursively, basically, inductively, I should say, once we start from the root down to the children, once we start from the root, we've received a message from all the children, so that means that we can send messages back to any of the children. That doesn't violate MPP. So therefore, the whole thing obeys MPP. So all messages obey the message passing protocol. And I think I've said all this stuff already. So here's some examples. Let's do a couple of examples and then take a break. The blue arrows correspond to the collect evidence. So there's the first message, the second message, the third, fourth, fifth, sixth, seventh, eighth, ninth, and so on and so forth. And then the red edges correspond to distributed evidence. How about this one? Does this correspond to MPP? You guys stare at it for a minute.
No.
So where no?
So we have message, actually.
Should we do it together? So we have 1, 2, 3, 4, 5. So far, so good, right? 6, 7, 8, 9. That looks good. 10, 11, 12, 13, 14. So collect evidence sounds good. Let's do distribute evidence in a different color, in red. So we do 1. Is that one okay?
Yeah.
Yes, because we received, at x1, we've received messages from all the children.
But shouldn't we be sending to X4 now? X1 to this?
So you're saying this is invalid? We've received a message from everywhere. So at this point, let's use a different color. We've received a message here, here, and here. So this is okay. So that means this guy's okay. In fact, all these guys are okay. 3 is fine. Now this guy's fine. 4 is fine, and 5 is fine. Right? We can always send any out of the root of the tree. 6 is fine. Now 7 is fine. 8 is fine. 9 is fine, and everything's fine. So collect distribute evidence works. Yep.
So for distributed evidence, if you do the collecting part right, then what are the restrictions on distribute then? Like what would be an error on this graph?
An error on this graph would be, for example, if let's say let me just erase all these red guys.
I think you cannot go 3 to 7
Yeah, there's a lot of potential errors. So let's say that I've done 7 before 6. Let's say I've done, so I've done 1, 2, 3, 4, 5. But now I've tried to do this. Let's zoom in on that. Why can't I do 7, that red 7? Because I haven't yet received this message. Right? I can only send a message when I've received messages from all my other neighbors. This guy 7 can't occur before 6 because if 6 has never occurred, we've never received a message from x1 to x4. That would violate the message passing protocol. Okay. And I was going to go over this example, but here's an example where you have redundant messages, and this would still be fine with message passing protocol. It's just that there would be some redundant messages. But I want to move forward because we're running a little bit late. So let's take a short break, and we'll come back soon. Okay, welcome back. One of the things I want to mention is a little bit about the name, collect and distribute evidence. And we haven't really talked at all about evidence. In the readings, I haven't posted this yet, but I will soon. There is this, obviously, a graphical model without actually evidence. Evidence is essentially when you sort of know the value of some of the random variables, and then based on those values of random variables that you know, compute the probability distribution of other random variables that you don't know. And so why is it called collect and distribute evidence? Because in general, evidence is sort of implicit, believe it or not, in everything that we've been doing. And all of the discussion about summing out variables can, with only a very, very minor change, be seen to be exactly the same as what you would do when you have evidence. And the marginals, what we're really getting, the marginals that we're actually getting are the followers. Like, we're not really getting the probability of xi and xj. We're getting the probability of xi and xj and x sub e, where e is the set of variables that are known to be observed. So therefore, we're sort of looking at it as x bar of e. And the way you can see doing this, well, first of all, like once we have this marginal, then we can easily, by summing out things, we can easily compute this conditional distribution, like the probability of xi and xj given the evidence by just normalizing. But the way that we sort of incorporate and deal with evidence is that when we do have an evidence node, we sort of multiply in a Dirac delta function, which basically is a function that's is sort of a function of two variables. Let's just write it down here for a second. There's xj and xj bar. So xj bar is the value of the evidence of xj, and xj is sort of the unclamped or unfettered variable. And what that delta does is it essentially annihilates all terms in the sum other than the one that corresponds to xj equaling the evidence value bar of xj. And so evidence is really just sticking these delta functions in the appropriate places. It doesn't change the summations because it's still, notice that it's still a function of these two variables, xi and xj. This whole thing here is still a function of xi and xj. And so you haven't changed, you haven't added any edges into the graph. You haven't changed the graphical structure. You've just changed what ends up happening with some of the zeros. And so if you add those deltas, then when you're computing these marginals, you'll be getting these marginals. And that's how evidence is dealt with. It's a very simple way of doing it. And so the notion of collect and distribute evidence is really that. It's like you're collecting evidence from wherever it happens to come from, wherever these delta functions have been added to the factorization. And then once you collect it, then you distribute the evidence. And so what ends up happening is that when you're all done with collect evidence and distribute evidence, all of the resulting marginals have had information propagated from all of the variables that are currently in evidence, or that are evidence, that are seen, that are observed. And that's why it's called collect and distribute evidence. But like I said before, it's sort of the collect and distribute evidence notion comes from usually the junction tree formalism, which we haven't yet seen, but we will soon enough. Okay, yep.
So is it kind of really easy to obtain those marginals, like in the previous slide when you mentioned that you have probability of xi, xj given some evidence? The probability of evidence can be some arbitrary parts of the graph, and so it may not really be easily computed, right?
Yeah, I want to talk about that. Isn't that similar to the question?
Again, similar to that only. I mean, it's just that you've written it as easy.
Well, in this case, I haven't addressed your question yet. So your question is, what do you do when, say, you want a marginal that doesn't correspond to a clique in the graph? We talked a little bit about that last time. I do have a slide on that, but we haven't yet come to that slide. But this is still under the case where the marginals that we're interested in are the edges. And the reason why I said that this is an important case, this is sort of the machine learning case, is because when you're doing learning, like when you're adjusting the parameters of the model in response to some data, under either the generative form or the discriminative form, if you go through and derive the equations, what's actually needed are the marginals over the cliques. Because the cliques correspond to the factors, and just by it being factored, the parameters are the things that are directly relate those variables only that are within a clique. You don't have any parameter. If you don't have an edge there, there's no parameter that corresponds to any direct interaction. There can't be any parameter that allows for there to be a direct interaction between two variables where there's not an edge. It's a restriction on the parameterization. And so when you're learning within this subfamily corresponding to the graphical model, you don't need the marginals other than the ones corresponding to the cliques. And so since, like I said, we're really not talking a lot about machine learning. There is a machine learning class that's occurring at the same time. And there's going to be some discussion on inference. Everything that we're doing, or a lot of what we're doing, sort of supports machine learning, which is basically adjusting the parameters of the model in response to some data. And we're basically talking about algorithms on how to do that. On the other hand, there's the scientific modeling question, which is that they want to know precisely how these two variables correlate, which is not a machine learning problem. It's a use of say, an existing model for a scientific question. I want to get rid of all this intervening, intermediary, perhaps distracting stuff, and I want to look directly at where the rubber meets the road between these two variables that I care about. How does color of the oranges affect the purchase price, right? Like if I make the color more saturated, do people buy oranges, or am I allowed to increase the price of the oranges if the oranges become more fluorescent or something? I mean, these are whereas the color and the price are maybe very, very indirectly related in the actual raw physical interrelationships between all of these sorts of things and the way in which one does that. So, but that on the other hand might be an interesting question that you are interested in, looking at the final relationship between color and price of oranges. But we will get that. In fact, since we're running behind, I want to skip. Basically, one of the things I wanted to talk a little bit about is the associated storage with each of these messages. There are these sort of alternative. I'm just going to mention that this stuff exists because I don't think we have time to talk about it. But it's in the write-up, and it's in the slides. But in addition to these messages, these kinds of messages, there are other message strategies that you can use that, for example, have various different trade-offs associated with their use. Like, for example, when you get sent a message, let's say you get sent a message mu of k to I, rather than just sort of having it sit there as a separate array data structure sitting at that node xi, what you can do is actually go ahead and update the entire potential. You can update the edge potential, and that means that the storage for that array can be seen as a temporary. You don't need to actually keep it around, because since you've updated the pairwise potential with the unary message, right? The unary meaning it only involves one variable, pairwise meaning it involves two variables. And since that's a temporary, you can sometimes reduce storage. But then the problem is that now you've lost that. You've changed the pairwise potential, and later on you might need to sort of divide it out so you don't have double counting. And so there are these other propagation styles, which I'm going to skip. This talks about the dividing out problem. And here's one propagation strategy. And there's another propagation strategy. But you should definitely be aware that these things exist. They're not really talked about that much anymore. There was a lot of discussion in the graphical models community about these different strategies in the 1990s and early O's. But there are these different strategies: the Shenoy-Schaefer strategy, the Loritzen-Spiegelhalter strategy, and the Huygens strategy. We will revisit the Huygens strategy again when we talk about junction trees. But basically, what these different strategies do, they're all message passing strategies, but they do various variations. They're all mathematically identical, but they use various different trade-offs between whether or not when you get a message, you multiply it into the pairwise potential and then divide it out later, or instead you keep it as a separate entity, and therefore you don't need to do any division. Some of them involve division, but maybe there's fewer arithmetic operations that you need to do, but on the other hand, maybe division is bad and you're on an embedded machine where division is slow. And so there are lots of trade-offs there, but I don't think it's key anymore. But getting to your question now, this is finally the slide of your question. So far we've said that we want each query to sort of be an edge. And so, for example, if we have a 4-node Markov chain, if the goal is x1, x2, x3, then we can just sort of sum away x4, and this is fine, right? This is basically an n squared, or sorry, an r squared operation, and we don't have much to worry about. On the other hand, there are cases where, actually, before we talk about those cases, basically, whenever it's the case that S, so we're with a tree graph, we have a tree graph. If it's ever the case that the thing that we're interested in, the marginal that we care about, is a sub-forest or a sub-tree, then we're guaranteed that we can still do it with an order r squared computation. And the way we do that is, in some sense, we root the tree at the sub-forest or the sub-tree. And I know that's not a conventional notion, but let's sort of depict this idea using this figure on the right. So we have this graph, and we have the thick blue edges. You can see that the blue edges corresponds to a subtree. It would be a subforest if it was a disconnected tree, right? But let's just say it's a subtree in this case. And so we sort of root it at the subtree, and then we sort of start sending messages to that subtree. So sending messages to the subtree means that we start away from the subtree and we start sending these messages, and we abide by the message passing protocol. So what we're left with is a marginal over this subtree. Okay. And in this particular case, S is equal to 1, 2, 3, 4, 6. And now, once we have this subtree, I mean, first of all, we have an efficient representation of the marginal, which happens to be a subtree, and also we've not spent ever any more than r squared, order r squared computation. Right? So the whole thing is still nr squared. But the real question is, and this is your question now finally, is like, what if S is not a subtree or a subforest? Like, we start with, say, a 3-node Markov chain. This is a very simple example of this. So x1, x2, x3. And the goal is x1, x3. That's the marginal we want. The only thing you can do is sum out of x2. That's the only thing you can do. I mean, that's what you do to get that marginal. And suddenly, you've done this r-cubed computation. Okay? So there's an inevitable fill-in edge that has occurred. And from the perspective of needing this marginal, computationally, we might as well have started from the larger family. So like, rather than just the Markov chain, why didn't we start from x1, x2, x3? So there's the Markov chain. But computationally, there's no penalty for adding that edge. Because if that was the marginal that we needed, the x1, x3 marginal, we would face an r-cubed computation anyway. So we could have computationally had that edge in there. Now, that doesn't mean that we want to have that edge. Now, can you imagine why we don't, even if it's the case that there's no computational detriment to adding that edge, why might we not want to have that edge?
Scientific understanding.
Scientific understanding is one. Good. There's one other reason, at least that I can think of. Yeah, exactly. The question was overfitting. The basic issue is like the number of parameters. Like if we're doing a machine learning problem, we start with the Markov chain family, which is a smaller family, right? And we have data, and we want to have a very constrained. Learning within a graphical model is basically like a constrained optimization problem, right? We're saying We're trying to find the maximum likelihood parameter estimates under the constraints that the probability distribution has to factor in this particular way. Right? It's a set of constraints. The fewer the edges, the more factorization requirements, the more constraints are required. If you relax the constraints, you have a larger family, which might get us back into this problem of either not finding a good solution or not having enough data or some overfitting problem, or there's less regularization or there's less constraints, and we might not do as well. Even though once we actually go to use the model, computationally there's no detriment to adding that edge. There still could be a detriment during either the sort of the goal of what the model is, the scientific understanding question, or the machine learning question, which is trying to find a model that fits the data. So, but let's try to understand a little bit better. Hopefully, does everybody understand that point? We mentioned that also a little bit last time. So let's try to understand a little bit better what is it that can happen? What is this sort of notion that there can be bad queries or bad computational queries? So there's this fundamental critical theorem. This is sometimes called Rose's entanglement theorem, which sort of helps us to understand this problem. So, so we're interested in a query S, right? And so to get that query, one way or the other, we need to eliminate all of these variables. Right? We need to eliminate everything except for S, right? Because we want the marginal over S, we have to eliminate. We have to sum out everything except for S. Okay? If it's a tree, and if S is a tree, we can keep eliminating. If S is a subtree, we can keep eliminating leaf nodes until what we're left with is S, which is that subtree. Okay? Now we have some elimination ordering. Again, this is the order that we choose to eliminate these variables, which, as we now know, is identical to an ordering of the messages. And let's say that sigma is this ordering. And just notationally, let's say for given vertex, sigma inverse v is the number associated with that ordering. So sigma is the mapping from number to vertex, and sigma inverse is a mapping from vertex to the number corresponding to the order that variable is that vertex is eliminated in. Okay. So here's what the theorem states, and I think it's critical to understand the statement of the theorem. It's less critical at this moment to understand the proof of the theorem, but let's make sure that everybody understands the theorem first. So basically, what we're starting out with is an undirected graph, G. We're starting with an undirected graph, and we've got an elimination ordering. It's just an ordering of the nodes sigma. And what that does through the process of variable elimination is it maps G to G prime, which is the elimination graph, where G prime is it's a graph over the same vertex set, but it's an edge set E, which consists of the original edges E plus the fill-in that was a result of eliminating the variables in that order. Okay, so F sigma are the fill-in edges added during the elimination order sigma. Everybody with me? Okay. Now, what this theorem states is the following. It says VW, which is a pair of nodes, right? So an edge is basically a pair of nodes, right? So we're saying that this pair of nodes is an edge in the reconstituted graph if and only if the following. If and only if, actually, let me use a different color for this so that I can designate the setup versus the statement of the theorem. So this is an edge in G if and only if there is a path in the original graph G with endpoints V and W, and where the nodes on that path are eliminated before V and W in the order sigma. Okay, so it basically means that the node, if we eliminate the nodes in the order sigma, that the nodes on the path between V and W are eliminated first before we get to V and W. So in other words, a mathematical way of saying it is the following. So we've got some path V to W in G such that for all of the intermediary vertices on the path, the number of each of those vertices on the path is less than the minimum number of the two vertices at the extreme ends of the path, which basically means that all of the intermediary vertices on the path have to be eliminated before, since the numbering gives us the ordering. Okay, so that's, oops, I don't want to do that. What I want to do is create a new page because I want to give you some pictures, or draw some pictures. So, okay, so we've got a vertex here, and a vertex here, and a vertex here, and a vertex here. Now let's say that the numbers I'm going to put next to the vertices are the ordering numbers that they're eliminated in. Okay, so let's say that this one's 3, and this one is 18, and this one is 2, and this one is 4. Okay, and here are the original edges in the graph. So there's no edge between this guy, say, and this guy, the purple and the red guy. That's way up in the corner, isn't it? Let me move this around a little bit. This is very much like whiteboard lectures because this is sort of going slow. So there we are, right? What's happening here? There we go. Okay, so the purple and the red. So the first thing we do is we eliminate some nodes. And eventually we get to this vertex 2, right? Because 2 is the first vertex out of those 4 that gets eliminated. What that's going to at least do is add this edge, right? And then this guy's gone, right? He's been eliminated. So then we eliminate whatever the third vertex is, and we get to the fourth vertex, and then it creates this edge. And then he's gone. Okay. So the reason why that remaining edge between 18 and 3 exists is because there existed beforehand a set of nodes that were eliminated before these two guys were eliminated. Or namely, all vertices in the path, this thing down here, all vertices in the path had a vertex elimination order number smaller than the minimum of the two extreme vertices in the path. Okay? And now what the theorem states is that an edge exists in G prime if and only if this condition is true. Okay. Now you might think, if this is confusing, you might think, well, wait a second, what about if I started with this structure? Right? I mean, there are no intermediary vertices on the path between those two things, so the condition is sort of automatically satisfied. Right? So whenever there's an edge in the original graph, there's still going to be an edge in G prime, just because, of course, all vertices on the path are going to be eliminated before. There are no vertices in the path, so therefore there's going to be an edge, and there's in a path. So what this means, however, from the perspective of, so there's the proof of this theorem, and maybe we shouldn't prove it in class, but I strongly encourage you, in fact, you to go through this proof. Okay, it's inductive on the vertex elimination order number, or the length of the path, depending on we're doing the original or the converse of the theorem. And the reason why this theorem is important is because it basically says, if you do an elimination order, what required fill-in will there be? So it's saying, like, if there are two vertices and there is no edge between these two vertices, if there is a path between them consisting of vertices that you've eliminated, that you will eliminate before you eliminate these two, there will be a path, there will be an edge between them, and that's going to be the problem in the case when you want to do this sort of scientific query, like in the Markov chain case. So here's another statement of the theorem. So in the worst case, S can become a clique, right? Like, you remember the star graph that we saw before? So we have a vertex there. Right. Suppose S consisted of all this stuff. right? So S world was the tire of the bicycle spoke hub, and the axis was the thing that you're eliminating first. So is there a path? Like if you eliminate this guy first, if you eliminate the red one first, that basically means that for all of the vertices along the tire, or the circumference of the thing, there's going to be a path consisting of vertices that are eliminated before you eliminate any of these. And so that means basically what we're going to get is a giant clique. Everything's going to be connected to everything, right, and so on and so forth. I'm not going to connect all these edges, but it's going to turn into a big clique. So if S was in that case, it just inherently would have to be an exponential computation to get S. So you as a scientist, say, basically have to sort of, if you have the ability to decide upon the queries that you want and also decide upon the graph structure that you're using, you have to make a trade-off. And thirdly, you want exact inference. This is all, remember, this is in the example of exact inference. We haven't talked about approximate inference yet. If you want exact inference, you decide the queries you want and you decide the graph structure, you have to make a decision. How much are you willing to pay? Maybe r cubed is not such a big deal. So if you have an occasional r cubed, if r is small, or even r to the fifth, if r is small, it's not such a bad problem. But on the other hand, at some point, you're going to be faced with an exponential explosion in the function, exponential in the size of the remaining query set that you want, if you're not careful. So the worst case, like I said, is when S can become a clique. We saw that in the star case. The best case is when there is no path between them outside of S. And when does that happen? When S is a tree. Right? Because when S is a tree, there's a unique path. And if S is the query that you want, and if S is a subtree, then the only possible path, since you want that marginal, that's going to be you're not going to eliminate that stuff. That's going to be the stuff that results after you eliminate all of the nodes. So if that's the marginal that you want, you're going to eliminate all of the stuff outside of S, which, because it's a tree, there's never going to be any path, because that would mean that there would be a cycle, both inside of S and outside of S, and that's not the case in a tree. So the typical case, I mean, what typically happens is that really depends. Sometimes this does happen. It's bad news for scientists who want to do exact inference and who don't have control over the graph. Like, let's say you're a scientific database query person and you have some graphical model engine, which is kind of like a database, and you're feeding these queries, and suddenly one of your queries takes several weeks to complete, and you're wondering, and you go ask your graphical model scientist, why is this query taking forever? This is why. And the graphical model scientist would have to say, sorry, you can't get, if you want this to be sped up, you have to do approximate inference. You have to approximate. Okay, are there any other questions before we move on to the next topic? Okay, so the next thing what we want to start doing is morphing more towards non-tree graphs. Okay, so we already defined the notion of that elimination. Elimination can be defined on any graph. And if it's a tree and you eliminate in something according to the message passing protocol, or you eliminate leaf nodes, you won't have any fill-in. We also talked about and showed examples where you can run elimination on any graph. And we also talked about there being an order associated with elimination, sigma. So sigma is called a perfect elimination order if it's the case that when we run elimination, there are no fill-in edges in the reconstituted graph. So F is equal to the empty set. F sub sigma is the empty set. Now we saw that trees are such that they have a perfect elimination order. But we also saw that not all orders are perfect elimination orders for trees. So might as well use the slides. So for a tree, there's always a perfect elimination order. And I think we know why at this point, right? So does anyone not know why? I think everybody should know why. Because there are always leaf nodes available. For an arbitrary graph, must there be a perfect elimination order? No. We know this. So the 4 cycle was one that we already saw. Okay. So now, I guess let's talk a little bit more about this 4 cycle. So notice, so using the factorization Markov property, or we could use a couple of others, which we haven't talked about. In the 4 cycle, there are 2 conditional independent statements that are being made. So let's look at this 4 cycle. What this is saying is that, on the one hand, x is independent, x1 is independent of x4 given the set x3 and x2. Right, this is like a separation property, but you can get this from factorization as well. So saying if I'm conditioning on x3 and x2, x1 and x4 are independent. The other thing that this is saying is that x2 is independent of x3 given x1 and x4. But there are no other conditional independent statements being made in this graph. And as soon as we run elimination, no matter what we do, when we look at the reconstituted graph, one of those independent statements is lost. In this particular case, it's no longer the case that x2 and x3 are independent given x1 and x4. The reason being that that there exists this edge. So this guy is now lost. So that extra independence property doesn't help us computationally in this graph. There's no perfect elimination ordering in this graph. And so somehow, because of the graph that doesn't have a perfect elimination ordering, it must be the case that if we were to do elimination, if we were to do exact inference, there are, from the perspective of computation, there are going to be extraneous properties. There are going to be extraneous factorization properties or conditional independence properties that are not useful because there is no elimination, there's no perfect elimination order. I mean, there's how many possible elimination orders are there in a graph with n vertices, n factorial? None of the n factorial ones lead you to perfect, which means that's impossible. That there's nothing that's going to be there's nothing that can utilize all of the properties that the graph states. Here's another example. Some elimination orders are worse than others. Like in this particular case, this is, by the way, I tried not to make this look like a cube. This is supposed to be a planar graph. This is not a cube on the left. Raise your hand if this looks like a cube. Okay, it is not. It is not. I played around with it, and no matter what I could do, it kept looking like a cube. So just think of it as a star or a cube or something. Maybe I should have put it on a circle. That would have helped. Made the edge a circle. That's maybe I should do that circle. I'll change the figure. But if we were to eliminate x4 first, then that would basically do the same thing we saw before. It creates a giant clique, right? On the other hand, if we eliminate some of these other nodes, we'll still have some fill-in. Like we saw, you can see some fill-in here and here. But we're not going to necessarily turn it into a giant clique. But is there a perfect elimination ordering in this graph? No, because no matter what vertex we eliminate, there's always going to be some neighbors that are not connected to each other. So again, this basically means that the family that we started with is strictly smaller than the family that we end up with. And this is why I like this family notation, because you can specifically see that we're only changing the graph by adding these fill-in edges. And so the family has grown. It's the same Markov properties, the factorization, but by adding these f's, these fill-in edges, we've strictly increased the family. We've made the family bigger. So this suggests that maybe there's sort of a notion of equivalence classes of families of models, which would be really cool, right? Maybe it's the case that if we could characterize and identify and work only within essentially the set of equivalence classes of families of models, namely those for which there is no elevation of the family by running the elimination process, or which we might expect corresponds to there being a perfect elimination order, maybe if we just worked with those families, we could just tell the scientists just work with these families, and then you never have this problem. Or maybe it's, you know. Okay, I'm going to stop now. Are there any questions? Because I think we're running out of time. We are out of time. Yeah, question.
Is there an algorithm that could find the optimal ordering when it is impossible to find the non-Abelian sequence?
The question was, this is an important question. Is there an algorithm to find the optimal ordering when it's impossible to find an ordering that has a perfect elimination, that's perfect elimination order? The answer to the question is yes, there is an algorithm. But the next question would be, do you want to use that algorithm in all cases? And sadly, the answer is no, because that algorithm can run in exponential time. Or at least assuming p is not equal to np, sorry. So, okay, I will see you on Wednesday.